So this is the part about the traction. The stress tensor multiplied by the normal direction should be equal to the applied force. So this would make sense. Now, the other thing is the stress equation of equilibrium. There's a set of equations that govern the behavior of the stress. I mean, the stress is not going to behave in a random way. It should obey the equilibrium equations. And this is the equilibrium equation just explained for the Cauchy stress tensor. Now, let us assume that you have this cube, and then you have the stress vectors on the surface of this cube. So this is one stress vector. Obviously, you can analyze this into components. I mean, this is the stress vector. You can produce the shear and the normal components out of it, but let us take it in the most general term. We think in terms of the general stress vector. Now you have the stress vector, or you have stress vectors acting on every face of this cube. This is an infinitely small cube, a continuum particle. Now these stresses will need to be in equilibrium with each other, but they would also need to be in equilibrium with the body forces. Let us assume that this body here is in motion, so it will need to observe the equation of equilibrium of momentum, the equation of a Newton. So you have the stresses. You can always convert stresses. I mean, this is the equation we need to satisfy. This is Newton's second law, conservation of momentum. And then the traction or the stress multiplied by the area. So this is acting on the top surface, for example. So you have the area, and then you have the one at the bottom, and you assume that both of them would be in equilibrium. All right, this is an assumption you make. So the one that is active on E1 and the one that is active on negative E1, you assume that they are the same, and you divide by the volume, and you would be left with this. I mean, I don't want to get into the details of the derivation for this. It's just that eventually you have the derivative of the stress, or the stress vector relative to the surface E1 with respect to x1, and so on for E2 with respect to x2, and so on for E3. So x3 is equal to the body forces if you have weight. So this would be expressed by the weight, so density multiplied by the ground acceleration. And then if you have an acceleration on top of that, if the object is moving or the particle is moving, then you have the acceleration, also the momentum resulting from the acceleration. You can simply write this using the summation rule. You see in this term, J and J is repeated, so you can use that. All right, so you know that the traction is basically, or the stress vector is the stress tensor multiplied by the normal direction. And this is written in terms of the indices. Eventually, you have this equation instead of this one. So instead of this, you have this one. And this is the equilibrium equation for the stress. I mean, if you just want to understand the concept of this, the concept is that you have the stresses active on, the stress vector active on each plane, multiplied by the area of this plane, should be in equilibrium for the stress that is active in the opposite direction. Okay, so this is basically the set of equations you have. So any stress tensor will need to satisfy this set of equations, and it will also need to satisfy the boundary conditions. And then you solve these equations together, you get the stress state within the material or the object you are interested in. Now, obviously, you are not going to solve the equations yourself. You are going to use the finite element method to solve this for you. All right, so just a very simple example about this set of equations. And I mean, it's probably lengthy, but it's very simple. It's just that T11, which is the first stress component in the matrix that you have for the stress. So this is T11, T12, T13, just like sigma 11, sigma 12, sigma 13, T21, T22, T23, and T31, T32, and T33. So These components, this one, and this one, we need to satisfy the first equation. These components, we need to satisfy the second equation. And the third, we need to satisfy the third equation. Okay, so this is just a simple example. Assume that you have the stress tensor to be given in this way. So first of all, you have x2 squared added to Poisson ratio x1 minus x2 squared. I should have I'll probably just copy this to OneNote. I think it is easier to see it there. Okay, so you are trying to solve, or you are trying to make sure that the equilibrium equations are satisfied for this stress tensor. I'm just going to write the stress tensor first. Use black instead. So you have x2 squared added to the Poisson ratio x1 squared minus x2 squared. The second component is minus Poisson ratio multiplied by 2 x1 and x2. And then the last one is 0. So you don't have any components in the third direction. So you don't have any components in the 1, 3 direction. So you have 2, 2, 2, 3, and 1, 3 are equal to 0. So I'm just going to write the 2, 1 now. And obviously, this is a symmetric stress tensor. So 2, 1, 2 and 2, 2, 1 are the same. So I'm just going to use the symmetry here. 2, x1 and x2. And 2, 2 is this one. This x1 squared plus Poisson ratio multiplied by x2 squared minus x1 squared. And then you have 2, 3 to be 0, and then 3, 1 is 0, 3, 2 is 0, and 3, 3 is the Poisson ratio multiplied by x2 squared added to x1 squared. Now the set of that we need to satisfy are in here. So first row we have T11 differentiated with respect to x1, 1, 2 with respect to x2, and 1, 3 with respect to x3. I'm just going to do that. So the derivative of this with respect to x1, this one will go to 0, this one will go to 0, and I will be left with 2 multiplied by the Poisson ratio x1. The derivative of the second term with respect to x2 is only this part. So this will go away, and this will be what I am left with. This minus 2 Poisson ratio x1 is equal to 0. So the third component is 0 away. And this will cancel with this, and the first equation is satisfied. Into the second equation, now again, the first term is with respect to x1, then x2, then x3. So this is with respect to x1, it is minus Poisson ratio 2 x2. X1 will just simply go away. And then this one with respect to x2, so this will cancel, this will cancel. I'll be left with 2 Poisson ratio x2 is equal to 0. Again, this will go away with this, and the equation is satisfied. And the last equation, I need to derive this one with respect to x1, it is 0. This one with respect to x2, it's 0. And this one with respect to x3. Now, it's only x2 and x1 in there. There is no x3. So the derivative of this with respect to x3, this is constant with respect to x3. So it's going to be 0 is equal to 0. And the third equation is satisfied.